Hello, everyone. Good morning. It's a pleasure to be here. I'm happy to have been invited to talk at this great event. So as was just mentioned, so I'll talk today about work done in the team on predicting aesthetic appreciation of images. So just a bit before we head on, so those of you who, most of you have probably never heard of Naver. So just to give you an understanding of why we're based in Europe and what we like to do. So we're an internet technology company headed in with our headquarters in South Korea. And we're quite a dominant player there in web search. And we have many other services that we provide to our users. So things like map services, shopping services, blogging, chat apps, and we have like a bunch of other services as well. So in Naver Labs Europe, so this is a recent lab that was that's been in existence. Actually, we have a previous history, but we've been part of Naver for about almost 2 years now. And we do research in many areas, including robotics, autonomous driving, augmented reality, user experience and design, and many other areas as well. And we're based in France. And so now I'm going to talk to you a little bit about what people have done in what I've done with colleagues in my team around data-driven approaches to aesthetic prediction. So for those of you who are, I think all of you probably have at least some familiarity with computer vision in general. In particular, you would know that computer vision involves, at least many successes in computer vision have tended to involve prediction of certain types of properties of images that are typically fairly objective. By objective, I mean that if you ask most people, what do you think about, for example, do you think there's a horse in this image? And if there is a horse, most people would agree with you, right? There would only be kind of a discussion if the image is particularly degraded, if it's very low quality, very low resolution, very poor lighting, and you can't really tell what's going on. But in general, most people would agree with you, right? So for things like object recognition, semantic segmentation, feature matching, for these types of problems, they've been quite successfully tackled using supervised machine learning techniques. So what we try to do in this bit of work is to really ask ourselves, can we learn the same types of models, data-driven models, for properties of images that are more subjective? So as all of you guys know, for data-driven problems, you tend to need two things, right? Especially because when I'm talking about data-driven, I'm really focusing on supervised data-driven approaches, right? So for those, we tend to need two things, two ingredients: a data set with annotations, hopefully robust ones, and also effective representations, right? Like representations of your data or your world. In our case, there will be image representations. So I'm going to talk to you today about two works that address these two, how can we get these two elements. Number one, the data that we need, and then number two, the representations that can leverage them. Right, so I'll start off with AVA. So this is a large-scale data set that we collected for this task. So I've been talking to you about aesthetic predictions. Let me just describe to you a little bit what exactly this means. In the community, in the computer vision community in particular, when we talk about aesthetic prediction, we mean, we tend to be talking about three main tasks, right? So number one, you might want to do what we will call like a binary classification task. So that means like, if you're given like a bunch of images here, you'd want to give each of them a label. I think this one would be appreciated by most people, and this one maybe not. You might also tell yourself, OK, it's a very kind of like very binary decision to make, and maybe the truth is somewhere in the middle. So rather, you might want to make a more fine-grained, more nuanced analysis, and you say, OK, rather than just give a label, I'd like to give a score. So for example, from a score of 1 to 10, what would most people think about this image? Would they find it nice or not, and to what degree, right? And then you might also say, OK, I want to be even more nuanced than this, because you might say an image can't be captured just in one number. You might say, OK, I want to have a range of scores, right? So I'd like to know kind of, if I asked 100 people what they think, what would be the distribution of the opinion of the scores? So these are the three types of tasks people tend to look at. So just to give you like a very quick run through of the basic pipeline for this, which like once again, many of you will be familiar with. So this follows a very standard kind of, let's say, semantic understanding pipeline for computer vision tasks. So you're given an image. You want to extract some kinds of features or some kind of representation of that kind of captures whatever properties you want to know about, right? So this would be like your feature extractor. Then you plug those into a prediction model, which you've trained previously. and it should give you some kind of prediction, be that a class label, be it a score, be it a distribution, something like this. Right, so in terms of features, there's been quite a lot of work done in the computer vision community about how can we extract features, how can we sort of craft features for this task. So you would imagine that people have tried things like trying to profile the color distribution of the images, things like saturation, things also like the composition of the images, do they have sort of like a nice placement of objects, these types of things. That worked pretty well. A bit after that, there was some work done in our group showing that actually even sort of generic features, meaning features that won't craft it specifically to kind of capture aesthetic properties, can actually still do quite well. In fact, it can do better than some of the more handcrafted stuff. And as more recently as you would probably guess, so deep learning has kind of superseded those previous approaches, at least in terms of performance, although sometimes interpretability is still an issue, as you would expect. And so, right now, most models tend to combine the two things I mentioned, right? They have the feature extractor and the model in kind of one pipeline that you can train end to end. So as I mentioned, aesthetic appreciation is subjective, right? There's no right answer. So that means that it's not the same, you don't have the same annotation criteria that you would have for a more objective kind of task, right? So typically, if you want to label a set of images of animals, you can ask maybe some animal experts, and you kind of ask maybe 5 of them, and they all tell you what it is, and you're happy with that. If you want to have a sense of consensus about aesthetics, you need to ask a lot of people, right? So this means that because of this subjectivity, the training data you need is going to be large scale in at least 2 senses. So you're going to need a lot of images, and you're actually going to need a lot of annotations per image, right? So this is kind of a key difference with other tasks. So given these requirements, where do we tend to get this data from? So if you look at public data sets that have been collected for this task, in academia pretty much, there are kind of 3 typical sources. So the first one is Flickr. This is nice because it's public, let's say, community, where you can collect images uploaded for many types of purposes, and people actually rate them. So you can get a sense of not just images, but how do people think about them. One drawback, of course, is that these annotations are not given specifically this is not necessarily an expression of people's aesthetic appreciation, right? They can be appreciating the image for different reasons, right? Photo.net is another community that's a bit more tailored to what we're interested in. So this is a community of, let's say, photography enthusiasts, hobbyists, amateurs, and professionals. So it's a bit more of, let's say, a narrow community, but very dedicated to photography. And they also have like a rating system where you can rate images that are put up. And lastly, there's DP Challenge. So this is an interesting community because it's in the framework, it's in the spirit of Photo.net, in the sense that people who put their images up tend to be, from pretty serious amateurs up to like super professionals, like very, very skilled photographers. And in this community, challenges are central. So the goal here really is for people to improve their photography skills, to get good feedback, to get constructive feedback, to become better. And because of this, they have challenges that they kind of put together in some regular basis, and then they get a lot of feedback, right? So this is actually, it's actually a very it's a very active community. There are lots of members, and so we're going to focus on this website because it has a lot of robust annotations. So just to give you a better example of what a challenge kind of consists of. So here's one called Skyscape with the description, make the sky the subject of your photo this week. So in this case, users are going to do exactly that. So go out and take pictures of skies from different stylistic aspects, different techniques, et cetera. And then during this process, they're rated on, right? So different people kind of rate the photos. And at the end of the challenge period, they will be ranked. And then, if you get a score with, if you get the highest votes, the highest average vote, let's say, you get, like a gold, like a blue ribbon. And you might get other ones as well. So here I'm just giving you some statistics at a glance about AVA, the data set that we collected from dpchallenge.com. So there's quite a few images, especially compared to your typical aesthetics database, with more than 250,000 images associated with about 1,000 challenges. And as I said, so one key thing is the number of votes you get per image. So you can see that there's about 200 votes on average, which is really it's a fairly robust amount of data for this task. There's also a few semantic annotations that come with the data set in the form of tags. So these are really not robust, although they can give you some interesting insights. Not robust because they're not free-form, so they're from a list. They're from a list of 66 tags that you have to choose from, right? Like in a drop-down menu when you upload your picture. And you can put up like max 2 tags. So that means that if you have an image that's relevant to multiple tags, you're going to have some false negatives in your tags. And then also people use the tags a bit inconsistently. They might have a different definition of what humorous means, and humorous is a tag you can actually put. So then you can see how one tag can have kind of wildly different types of content. And then there's also a few style annotations and some textual annotations as well. So this is interesting. So this starts to give you a hint of some of the challenges you might have working with this type of data. So if you take all your images and you just plot a histogram of the mean score that was given to each image, there's a huge bias, right? So what you would expect. There's very few images that are appreciated by most people, that there's a huge consensus it's good or bad. Like most images are somewhere in the middle, which means that if you want to train with this data, you're going to have some biases there, right? And also there's a bias in the content. So very often there's a lot of, you see a huge bias towards photos with nature, topics, landscapes, still lives, and then there's kind of this long tail. I'm not actually even showing all the tags, but there's like a long tail of other categories. And then so here, I'm just giving you a sense of what the score distributions look like for each of these images. So as I said, every image has about 200 scores that we're giving to them, 200 votes. So this is sort of giving you a sense of what the distribution of those votes look like, right, on average. So what we did here is we kind of clustered all the distributions we had, and now I'm showing you some prototypical score distributions. So you can see that most of them, if you tend to have a mean score that's kind of in the range, in the midpoint of the rating scale, then you kind of have something that looks like a Gaussian distribution, but then you have a few outliers, like on the extremes of the rating scale, right? So if you have an image that's not rated very well or rated extremely well, then they tend to have this more of a gamma distribution. Okay, so I will just go through this. In the interest of time, I'll skip through this very quickly. This is just saying that we try different distributions to model these the scores, and that, as I just mentioned, like the Gaussian one worked best in general. But then if you had images with kind of extremely good or extremely bad scores, then a gamma function tended to work better. Right, and then here it's also a bit intuitive, the sense that if we looked at the variance of the distributions to have a sense of how compact were the scores, how much consensus was there. As you would expect, stuff in the middle there tends to be a high amount of consensus, but then when you start to go to things that are extremely good or extremely bad, it's a bit more, the variance is higher. Okay, so that's like a rapid look through the AVA data set. Now I'm going to just describe to you how we use this to train a deep architecture for unified aesthetic prediction. And I'll explain to you in a second what I mean by unified. So once again, I'm showing you like the different tasks we might want to tackle, right? So by classification, regression to a score, or a structure prediction task. So, but if you think about it, so in all of these data sets, including ours, when people come up with like a binary label, very often what they do is they get this label by, it's like a derivative of a raw score distribution. So normally you start off with a distribution, and you might calculate a mean score from that. And then if you want to do binary classification, you might just threshold that score, and you say, okay, if the mean score for this image is 5.5, is above 5.5, then it's good, otherwise it's bad. So what we try to work on in this is to look at the distributions themselves. Because number one, you're avoiding adding noise to your annotations by having this threshold where it's pretty arbitrary, right? It's a bit hard to say why is the mean of the ratings, why is the midpoint of the rating scale the point where you say something's good or not. Also, there's like a lot of images there. Because as I showed you guys, because the distribution is normal of the scores, if you put like a threshold in the middle, you just sort of a lot of scores on that boundary, right? So you get a lot of noise in the annotations. So to avoid this, and also to have just more information, we're interested in predicting the distributions themselves, right? And then here you can see an example of two images with both of them having the same mean score, but having pretty different score distributions, right? So this is kind of interesting information that you might want to keep. So there's been previous work on this task. We're not the first one to have looked at this. I won't go through this in too much detail, but just to say that We will diverge from these works a little bit in the fact that we really want to understand also, when we're training these models, how can we leverage the semantic information of the images themselves? So why would we be interested in trying to leverage semantic information? Because we know that aesthetic properties are dependent on the content within the image, right? So just to give you a sense of that, if you look at these 3 sets of images, these 3 rows, the first one has like architectural content, the second one has animals, the third one has flowers. And you can see that the aesthetics of them are quite different, right? So you can see that in the first case, something that's rated highly. So these are all with very high mean scores, right? And so for these images that are highly rated, for example, for architecture, there tends to be like a very high dynamic range of the images. You tend to have a lot of playing around with vanishing points and leading lines. In the second one, you have this kind of macro effect where you have like a sharp foreground and a fairly blurry background. So you can tell that depending on what's in the image, the styles and the techniques that people use, photographers, are quite different, right? So we wanted to kind of bias our model to take into account semantics in order to predict aesthetics better. Right, so as I said, there's a complication with this in the fact that we don't have really good semantic annotations, right? Because as I mentioned, we have these kind of tags that photographers give their images, but their tags can be incomplete. They're not really used consistently. So what we decided to do is to use an approach that's inspired by model distillation. So this is a technique that was introduced by Hinton et al. And the idea of this technique is to say, I have a model, right? Some kind of prediction model. In their case, it was a deep network, which is doing something really well, right? In this case, it's doing classification very well, classifying images from the ImageNet dataset. It's been trained to do that super well, but maybe it's very huge, for example, and you want to be able to do the same thing, but with a smaller model. So then you take a student network, and you train the student, which is typically smaller, not to do the same task, but to replicate the predictions of the teacher. So the student is not getting trained on the binary ground truth of the original data set. The student is getting taught to to make the same predictions. So for example, if the teacher network gives you, outputs to you like a softmax probability distribution over a set of classes, then the student will be trained to replicate that softmax probability distribution rather than the binary labels. So the motivation for that work was to do model compression, as I mentioned. In our case, what we did is we took a teacher network that was trained for classification, and then we considered these the probabilities, the predictions given by this network to be some kind of like a semantic signature. You can think of it that way. So basically, if we take an image from AVA, which doesn't have any semantic annotations, but you ask yourself, what would be the probabilities of a set of classes for this image? That gives you some sense of what's in the image, right? It gives you like kind of a semantic understanding of that. So then we use this as our semantic ground truth. And what we did is we trained our model to predict this data in order to give it a better initialization for our final task. So I'll just go into that in some detail now. So the first step we did is we took this model, and we used ResNet, for example. We took all our images in AVA, and then we applied the model to it, and that means that for every image, we got an associated set of softmax probabilities, okay? So we can think of this as kind of like a pseudo ground truth. In the next step, we took our architecture that we designed for our task of aesthetic prediction, and the main feature of this one is that it has higher resolution to get higher, let's say, more fine-grained local information. And we trained it to predict the softmax output that we just got before, right? So this is the pseudo ground truth that we get from a previous model. So what this is going to do is going to bias the features towards retaining information about the semantics of the images, okay? And then now with this set of weights, we use this to fine-tune our final model for the task, our end task, right? Which is to predict this score distribution, okay? So it's really kind of like a progressive fine-tuning procedure. So we ran some experiments on this on several tasks. I'm not sure they're super interesting, so I'll just say that I'll just give you the executive summary. So the fine-tuning approach works, okay, of course. And then some maybe more interesting is the qualitative stuff. So So what I'm showing you here are images from AVA, from the test set, which has the highest and the lowest mean scores, okay? And so I'm showing you the ground truth distributions in black and the distributions that were predicted by our model in green. And you can see that it tends to do like a pretty decent job of predicting kind of like the general trend of the distribution. You can see also that it's the predictions are not exactly the same, but they're quite similar. So it kind of indicates that our model is learning almost like a template of distributions matched to kind of aesthetic properties. So that's where things kind of work. So of course, things don't always work. As you would expect, the model tends to not do so well for images with let's say, kind of outlier distributions, right? So as you guys saw in the initial part, the data set itself is quite biased. So it doesn't see stuff like this very often, and so it just doesn't do very well when it sees it, right? So when you have these very kind of skewed distributions, it tends to regress a little bit to the mean. And so so in terms of interpretability, so as I mentioned before, end-to-end models tend to not be so interpretable, right? So we wanted to have a sense of not just why something was being predicted as highly aesthetically pleasing, but also why, right? So to get some sense of this, we wanted to kind of investigate the model a little bit. So what many works do is try to look at the weights that are learned by the model to have some sense of what is it really trying to, what kind of patterns is it trying to recognize. But for aesthetics, it's a pretty high-level concept, so that approach doesn't tend to work so well. So what we proposed to do was to adopt a kind of adversarial approach where we asked ourselves this question. We said, if we take an image, it has a specific predicted distribution, let's say. If we would like to make it worse, if we'd like to make the image to be predicted to be worse, what gradients would we need to shift? And which regions of the image would we have to modify to make that happen, right? So this kind of gives us a sense of what regions of the image are kind of are important or influential in changing that decision. So if we did that, and then here I'm showing you some qualitative results. So the results are not always so clear. In this case, you can see that some examples that we brought up which show that there tends to be like a bias very often we saw towards, for example, things like faces, then also to foreground objects that are pretty sharp, which makes sense because we explicitly tried to bias our model towards kind of taking into account semantics of images, right? So just to summarize, we started off asking ourselves the question, can we do anything interesting? Can we really learn in a data-driven manner to replicate or at least to understand aesthetic appreciation, let's say? And we found that yes, we can if we have like the right data sets and if we have the right types of image representations. So the major challenge in this work is really bias. And there are many different types, right? So number one, as I said, most of images are rated as kind of average. Also, the semantic content tends to be biased. And lastly, the raters themselves are self-selected, right? So this is not, as I mentioned, this community that we looked at is a community of let's say, photography professionals. So they're not like the average you and me, right? So their notion of what's a good image would be different to the average person. And that's it. Thank you.
Are there any questions? Yes?
Thanks for this very interesting presentation. You mentioned about the importance of content,
yes.
But I guess context could be important as well. Maybe a potential application is for social feed, right? So if people see 10 images of a landscape and then one flower, they might like the flower.
Absolutely.
Whereas if they see 10 flowers, the standard for an aesthetically pleasing flower is going to go up. Have you looked at that at all?
I completely agree, and this is another thing that we really try to think a lot about in the data set, because there are even things like when we were collecting this, when people are rating images, what are the order the images were listed in when they were rating. Some images may have been rated like in a completely different context, and then the ratings are different. Were things rated on before or after the challenge finished? Because you can actually rate after the challenge finished. So there are many contextual issues that can change this. So this is something that we didn't manage to tease apart, but I'm sure it affects the results in some way. Yeah.
Okay.
Hi. You mentioned that aesthetic is very subjective, and you try to leverage it by predicting not the exact score but distribution. But have you tried to solve the task differently when you have an image and a user profile, and you try to predict this user's score for an image? So do you have any intuition on how well it can perform?
So we don't, but that's an interesting question. And there's been works that have done that. We haven't, because particularly with this line of work, because we don't have per user scores. So we can't profile a user. But there have been works that do that, and yes, they found that. In particular, there's been a fair bit of work that has tried to, at least for things like prediction, to weight different users differently, because they might be a bit skewed, right? So for example, there might be the type of person who's very enthusiastic and very positive and rates things in general like a bit more highly than others. So that type of work has been done. Personalization has been done as well, but I think it's a bit hard to get robust models just because of lack of data. This is my understanding.
Right. Yeah, thank you very much. So yeah, I think art is one of my favorite areas for the application of deep learning in the humanities, right? Quick thought. I mean, I think you touched on this by, perturbing the image to see what could make it, more pleasing or what was contributing. Have you considered, or do you think it's feasible to add, a decoder or a generative aspect from your feature space to, like you would train a variational autoencoder or something, right? Where you could actually then navigate in that latent space to make things, you could automatically make your pictures more beautiful, for example, or something like this.
Yeah, so I wish I had time to talk about that. I actually really ran out of time to even talk about what I wanted to, so I'm sorry if I went a bit fast. So definitely that's very interesting. There's been work on generation, and in fact, we've done some recent work on that, which is currently under review, so I didn't discuss it. But yeah, you can definitely do that. So I can tell you that there's been work that recently we've done, and there's been a bit, not much, but some work showing two things, showing that you can just generate from some sort of noise variable, things with different aesthetic properties, and that also you can do manipulation. So manipulation is manipulation or augmentation or enhancement. So you can sort of have an input image and then try to let's say disentangle like what's the content versus what are the aesthetic factors, and then you can try to play around with those aesthetic factors to give you something with a different aesthetic quality. Yeah, so exactly. Yeah, so that's quite interesting. Very few things have been done there, and I'm actually pretty interested in moving in that direction.
Okay, no, thank you. Yeah, you can imagine trying to look at the positioning of all these images and different types in this latent space too, and as you said,
exactly, as you said, navigating through, by changing some latent variable. Yeah, exactly.
All right, thank you.